Welcome to lab, everybody. Sorry we're running a couple minutes late today. They had an interminable meeting that had an agenda considerably longer than the time allocated for it. So that now being in the past, we'll get right to work. Today's lab is about text prediction. This is using the TRI data structure that we have been studying over the last class period and change. So let's go over the overall concept or idea of the lab, and then we'll get into some details. Keyboard assistants suggest words when you're typing, and this is especially popular on smartphones. Many different data structures can be used to assist with this, but the specific one we're going to look at is the TRI. So what's nice about the TRI is that it represents words in a hierarchy based on their prefixes. And by representing them in that way, given an introductory letter or two, it can predict what all the possible completions are from that word, provided that the word is present in its dictionary. So, so in this lab, you're going to be implementing code in the TRI class, and it's going to be making use of some other classes to see what methods are available. And I'll walk through that stuff with you in a few moments. I first want to give you an overview of what you'll be doing, and then we'll look at the details. Step one is to implement a size method, which just counts how many TRI nodes have is member set to true. I recommend doing this recursively. Step two is to implement two methods, get child with and find. Get child with is not a recursive method, it's a convenience method. It gets the child corresponding to a given letter one level down, or returns optional.empty if no child node corresponds to that letter. It's not recursive, it's just a convenience method. You'll be using it. Find is a helper method that follows an entire string downward through the TRI, taking one step down per character. It returns a stack of TRI nodes that trace the path that corresponds to the prefix. If the prefix itself is not present, it will contain all of the leading characters of the prefix that are present. So for instance, let's say the word ant is present in your TRI, and you do a search on anteater. It'll return the ANT nodes. You'll get those. In my implementation, I used one of my favorite classes in the standard library, actually. It's called Array Deck. What is an array deck? A deck is a double-ended queue. It's actually an abbreviation for that, double-ended queue. In other words, a deck is a combination stack queue in a single convenient data structure. And so decks can be really nice to work with because you can treat it as a stack, you can treat it as a queue, and you can even manipulate it both ways and add and remove efficiently to both ends. The array part is that it's implemented using a circular array, much as we did for queues oh so long ago. Like it feels like in a lifetime ago, doesn't it, that we implemented queues in this class. So uses array deck. All right, now find doesn't care whether is member is set or not. It's just exploring the TRI to see what nodes are present. Okay, whether is member is present or not is something that it helps us with later on. In step three, so in step three, you'll use find as a helper method for all three of these. Contains checks to see whether a given string is contained in the TRI. And be careful to remember that contained means that isMember is set at the node that terminates the sequence of edges corresponding to the characters in the string. And this is very much along the lines of what we examined in class yesterday. You'll implement add, which adds a new word to the trie. So there you'll be using find to see how far down can I go, and then you start adding new nodes for the letters that are left. And that's why it's important, looking back, that find doesn't care if the prefix isn't present. It'll give you everything it's got. So the point is you use find, it gives you everything it's got, and then if you need to add more, you add more on your way down. And then implement a simple version of remove. Is the basic version we discussed in class yesterday, where you find the end of the word to remove and then set isMember to be false. That semantically removes it from the trie. And so that's step 3. So at step 3, you've got a pretty functional trie working as an implementation of a set for a string. Step 4 is what really makes it useful, implementing in order and successors to. So in order performs an in order traversal of the trie rooted at a given node. And we, again, discussed in class yesterday how to implement this. Successors to is what we're going to be using to find the suffixes that correspond to a prefix that are members of the trie. So the idea of successors to is that you're going to use find to find what node your prefix ends at, and then you just use in order to look at all of the children of that node, and that gives you all of the successors for that prefix. And that's what enables the text prediction to happen, is successors to. Then if you get all of that done, step 5 is to implement the space-efficient version of remove, which deletes unneeded trinodes. And what find gives you, that stack of nodes, will help you with that task. And so then here is the scoring, and that's basically the lab. Let me give you a brief tour of the source code. So this program is organized into 2 packages, the core and the GUI. The GUI displays a fairly simple little user interface, which is compiling as we speak for some reason. All right. And so you can type out something here, and ultimately, once successors to works, you'll see all of the completions here. Now you might wonder, where do all the words come from? Well, as it happens, there's this text file present in the package. It's called wordsen.txt. It has a few words in English. By a few, I mean 109,583 words. This, in fact, is derived from an online list of words that are eligible for use in Scrabble. In case you're wondering where this comes from. Yeah, at some point, some poor soul typed in 109,583 words. Or maybe it was a couple of poor souls working together. In any event, being poor souls, let's just hope that they have less time in purgatory than they did before. Anyhow, let's look at the trie class. So this is what's provided for you. Each trie object contains a Boolean which indicates whether or not the sequence of characters leading to this node constitute a member of the set of strings that it represents. Then we have a class called sorted array map, character comma trie. So sorted array map maps a character to a trie. That's the character, which will then point to another trie node, which has all the nodes that include that character as part of their prefix. Sorted array map is included for you It's completely implemented, but you're going to need to use it quite a bit. And so let me give you a brief tour of what it contains. Add is very important. You give it a key and a value, and it's now stored. So this is how you're going to say, this letter doesn't have any nodes associated with it. What am I going to do? I'm going to use add with that character and a brand new try node. What else does it have? It has remove, which you would only use on step 5 of the lab if you get there. It has get. Get returns an optional. There will be a value returned if that key has a value. Okay? If that key does not have a value, it'll get your optional.empty. Okay. And then it's got an iterator. You can actually iterate through it. So in other words, you could write a for loop over a sorted array map as if it were an array and just use the for loop directly on it. And it'll tell you the size as well. So very, very useful class. You're going to be using it a lot. Make sure that you get comfortable with it. Within the try class itself, I have provided the constructor. I didn't think too hard about the constructor. Note that isMember is initially false. You'll need to change that immediately in certain situations. Size, remember that's the first thing you're implementing. GetChildWith is the non-recursive thing that just examines your array in your current node. So the whole point of GetChildWith is that you don't have to, you can write all of that sorted array map code once and include it in GetChildWith for finding purposes. Then this find method is the absolute crucial backbone method to make everything work. You definitely want to work hard and carefully on that. Then contains, add, and remove are those step 3 methods. Then you've got in order, and I've got a couple of hints there. So you're finding all the words in this try in alphabetic order. You're going to recursively visit all of its children, adding their found words into an array list, prepending them with the in progress prefix. So what I want you to do here is write a recursive helper method which has as a parameter that current prefix as well as the array list you're loading up with material. So this is going to be the pre-order traversal strategy. In class, we talked about both a pre-order traversal strategy and a post-order traversal strategy. I would like you to use the pre-order strategy. Morgan, put your phone away immediately and do not take it out again during lab. Then successors to is going to be making use of a couple of methods you've already written to get you all possible completions of the prefix that's coming in here. And that's the lab. Any questions? Happy coding. Jacob and I will be around to help you out.